Okay, let's move to the tutorial itself. I'm going to stop my video because it's only the iPad, and let me share my screen. Okay. So yeah, convolutions galore. That's basically what I'll talk about. Well, galore is a bit of a stretch here. I'm actually going to talk just about two kinds of convolutions, and one of them is the standard one that we're all used to from you know, from some applied math class, if we've ever taken one. And the other one is the spectral convolution, which was discussed briefly in Matthias Fay's Q&A session, which is a type of convolution on graphs, which is somewhat different from the message passing convolution that Matthias was describing, but you know, on the other hand, they might be more similar than one thinks. I don't really know the connection between them all that well. But so this tutorial is, you know, me being coming from a mathematics background, this tutorial is going to be pretty pretty kind of maths in the sense that it's a pen and paper, or in this case, pen and iPad tutorial. And we're just going to look at mainly a very simple example and try and connect these notions of convolutions, understand them a little bit better. So without further ado, let's dive into it. So one type of convolution, the one that is most people are familiar with, is the standard convolution on Rn. Just one second. Right, so if you have two functions on Rn, you can define a convolution between them by basically flipping one of them and shifting it around, and multiplying by the other and integrating the result. So if you have two functions in Rn, then the convolution evaluated at point x is the integral over Rn of f of y g of x minus y dy. And just a little caveat here, of course, for this integral to exist, these functions have to satisfy some constraints, but I'm just going to pretend that these constraints are just always satisfied and ignore them. It will be the case for most functions that you try to convolve. I mean, as long as this integral isn't obviously non-existent, so as long as the functions decay appropriately at infinity. You know, maybe a slightly more computationally tractable version is the discrete analog. So on z to the n, so on a infinite square grid. Well, just for concreteness, let me work on z2. And in that case, we have the convolution formula like this. So here, instead of the integral, we have the sum. And have f of uv and g of a minus u v minus v. Again, for this sum to converge, we need f and g to satisfy appropriate conditions. And it's this discrete version of convolution on our square grid that that is used in convolutional layers of a standard convolutional neural network. Now, I've written out here what these layers do in full, but I'm not going to go into it, into all of it, as it contains a lot of details that are not particularly relevant to the points I'm trying to make. But basically, we can think of an image, and let's, for simplicity's sake, think of this as a grayscale image. So we can think of it as a function on the square grid. We can think of it as a function on the infinite square grid that's just 0 outside of a finite square, and otherwise on this square it gives the grayscale values of the pixels there. And then we have a filter. This filter that I'm calling psi here. So let's, for the sake of an example, suppose psi is a 3×3 filter. So that's just another function on Z2. And being a 3×3 filter just says that, well, it's supported on these points. And so what the convolutional layer does is it will produce a new function on Z2 supported on the same grid where the original F was supported. And it will have, it will take F and convolve it with psi. Well, not exactly psi, it's a small technical detail that we have to actually convolve with psi check, which is just defined, well, psi check of AB is whatever, psi of minus A minus B. But apart from that small detail, we'll convolve F with psi, and we'll then apply some nonlinearity, which doesn't affect our discussion at the moment. And so just to really drive this point home, we can, because psi is a 3×3 filter, we have this infinite sum, but the psi here is only non-zero for u, when u is a minus 1a or a plus 1, and the same for v is either b minus 1, b or b plus 1. So we just have this this summation here. So we get this finite sum, and this mathematical expression is exactly the corresponds to the usual picture that we see about a convolutional filter being applied to an image, in which we have a the produced feature values at the point AB is, well, you take the filter and you center it. So suppose maybe this is the point AB here. We've centered the filter there, and we just multiply the values of the filter with the values of the image, and this becomes our feature value in the feature space. And an actual convolutional layer has many filters stacked on top of each other. Now, let's just make a few simple observations here. The first thing is that the object that really helped us define this this convolution on Rn or on Zn was the existence of a kind of shift operator on Rn or on the square. So we're shifting x by minus y. So that's and then plugging it into G. And it's these shift operators that are behind a lot of natural notions of convolution. And this is a shift operator acting on the space, but if you want to act on functions on the space, the convention is that you would you just precompose them with a shift in the opposite direction. So here you can see this is the shift operator TAB applied on a function f, and that's the same as just applying the opposite shift to the arguments of the function. And this shift operator is what allows us to define the convolutions, right? So we can just write convolutions as f star g of uv is just the integral over well, let's stick to Z2. So this is just a sum over AB of f of AB T AB G of UV, right? And moreover, if you think, so the convolution is a map that takes two functions and produces one, but if you fix one of them, so for example, like in convolutional neural networks where you can think of the filter, even though it's a learnable parameter, it's a fixed thing, so it's the same filter that gets convolved with every image, say at inference time, so once the filter has been learned. So you can think of the map just that takes a function f and just sends it to f convolved with g, and that map, it's a simple exercise to check that this map is shift equivariant. So whether we shift before, so if we take TAB and then convolve with G, that's the same as what we first convolve with G and then you apply TAB. And therefore, because a convolutional layer in a CNN is basically a convolution with a filter with some nonlinearities applied afterwards, this shift invariance shift equivariance is preserved, and so the feature values, if you shift an image, the feature values will shift accordingly. And so in that case, in that way, geometric information about position of objects gets passed down into the hidden layers. Now, however, on a graph, on a general graph, we don't have a shift operation, and so we can't really define this, or at least on most graphs, we don't have a shift operation, and so we can't define a convolution in this way, and so we have to resort to different ways of trying to define it. And Matthias was explaining earlier about the message passing approach, which aggregates features from neighboring nodes into a node and updates its state. But there is a different approach for doing graph convolutions called spectrograph convolution. I heard from the Q&A that this approach isn't maybe used so much anymore because of its computational costs. I'm not particularly an expert there, so I don't know exactly what the computational costs are and how they're offset by other features of this method. But what I was more interested in is when I first saw this method, the definition seemed pretty removed from the definition of convolution that we just discussed, and that was kind of more familiar to me. And so I wanted to understand what is the what's the connection between the two, and how far does this analogy take us. So let me define the spectral graph convolution for you, and then I'll discuss the connections with what motivates this idea. And by the way, if you have any questions or at any point you want to stop me for some reason, please either raise your hand or interrupt me. I'm very happy to answer your questions. Okay, so let's dive into this spectral graph convolution. Suppose you have some graph V. V is the set of vertices, and we assume it's a finite graph. It has n vertices, and it has a set of edges E. And for simplicity's sake, we can assume that it's an undirected, it's a simple graph, so no multiple edges between vertices, and we won't assign any weights to the edges. There are extensions of this these spectral ideas to directed and weighted multigraphs and so on, but just for simplicity's sake, let's stick to this simplest case. Now, on a graph, there is an operator, which is a linear map delta, going from Rn to Rn. But the way to think of these Rn's is basically as functions on the graph. Right, so oops, sorry. Functions from gamma to R, real or complex valued functions on the graph. And the graph Laplacian, so it's a linear map, and as a matrix, it's given by it's D minus A. Now I should mention there are different versions of the graph Laplacian, but this is the one that I will concentrate on. And A here is the adjacent matrix of gamma, which you probably know. So it just says that it's either 1 if there is an edge between vertices I and J, and is 0 otherwise. And then D is the degree matrix of gamma. So this is a diagonal matrix, which is either the degree of vertex I, if I equals J. So the degree is the just the number of edges that go into that vertex, or it's 0 otherwise. So because we assume that our graph is undirected, we have that the adjacency matrix is symmetric, right? If there's an edge from I to J, then there's an edge from J to I. And with a little bit more, oops, that was the wrong tool. With a little bit more work, we can show that it's a semi-positive definite, so all of its eigenvalues are non-negative. But the fact that it's symmetric tells us that we can diagonalize it. And we can diagonalize it orthogonally, so that there exists an orthonormal basis of eigenvectors. Yes. Like that. And so any function on the graph, we can now express it uniquely as a linear combination of this eigenbasis. So each of these VIs are, you can think of them either as functions on the graph or as vectors in Rn, or possibly Cn. And so any function can be written as a linear combination of these VIs, and so we can write it as 1 to n, and I'll denote the coefficient in front of the mth eigenvector by Cm of f. Okay, so with that information in mind, we can now define this the spectral graph convolution of these two functions, and is defined as so if you take two functions on the graph, it's defined by, it's supposed to give me a new function, and what we do is, well, we just multiply their coefficients together, and I need this to be a function, so the coefficient in front of Vm of the new function. So another way of writing this is the coefficient in front of Vm of the new function is just the product of the coefficients of the old ones. Okay, and I'm just going to make one notational change here. Because we chose this basis B here, I'm going to put a little subscript B under the convolution operator, and the kind of the dependence on this B is going to be pretty much the main idea of the rest of the talk. Now, okay, so this is the definition. At first glance, it's pretty removed from what the kind of convolution we were discussing before that used this shift operator on the plane to convolve two functions. And the motivation for this, for the spectral convolution, actually comes from the circle. So let's consider what happens if we take the circle as a one-dimensional manifold. The particular inclination of it that I'm thinking here is as complex numbers of unit length. But actually I'm going to parameterize it just for notational convenience like that. Right, so it's just e to the 2 pi I theta. And now notice that a function on the circle is the same thing as a one periodic function of this angle theta. So whenever I discuss functions on the circle, I will write f of theta instead of f of 2 pi I theta, just for convenience. Now the good news here is that on a circle we do have a natural shift operation, right, which expressed in terms of the angle theta is just shifted by a little bit more. So in the parameterization above, this corresponds to counterclockwise rotation by s. And so we can use this shift operation to define a convolution. So if you have two functions from the circle to R, we can define the convolution as f star g of some angle theta, and we just integrate over the circle, and we shift this second function by the variable that we are integrating over. So on a circle, it's a manifold. It's not Euclidean space, but we do have a nice shift operation, so we can define a very natural convolution. And on the other hand, we also have a Laplacian, like in the graph case. There is a Laplace operator, well, technically a Laplace-Beltrami operator, but at this point, the Beltrami is just a minus sign. And it's just given by minus the second derivative with respect to theta. And then something that we know and love is Fourier series, and this is where Fourier series come from. They are we have the Fourier basis. So these are functions on the circle, or in other words, periodic functions on the real line, defined like so, and indexed by the integers. So for each m, we have this Fourier basis element, and it's immediate to see by just differentiating these functions that they are actually eigenfunctions of this operator. So indeed, you can see that with the conventions that we have here, nabla of chi m is 2 pi m squared chi m. So it's an eigen vector of this operator with eigenvalue 2 pi m squared.
Minus as well?
No, because I have I squared that squares to -1, and then I have the minus from the operator itself. Right?
Okay. Yeah, I missed that. Thank you.
So now, one more thing, the standard fact from Fourier analysis is the fact that these functions are actually form a unitary basis of for the square integrable functions on the circle, and that's a mouthful. But basically, it says that any reasonable function on the circle can be written in a unique way as a sum well, an infinite sum here, overall m and z, there is some unique coefficient times these Fourier bases. So this is just the standard Fourier series, the way that we are used to expressing periodic functions on the real line in terms of sines and cosines. This is just rephrased a little bit in terms of functions on the circle. And then the crux of the matter here for us is the convolution theorem, which says that, well, we already have a convolution on the circle defined by this shifting operator that exists on it. And the convolution theorem here says that, well, if we convolve using the shift operation, then express it in terms of the Fourier basis, we end up in the situation where the Fourier coefficients just multiply. Okay, so ignoring all the technical details about what the function should satisfy and manipulating these sums and integrals formally, this convolution theorem is pretty easy to check. And so this is where the spectral graph convolution analogy comes from, right? Basically, just we copy the formula from Fourier series into graph world. And the one very reasonable question you might ask is, how much of a leap is this analogy? And in general, as I said, there is no shift operator on a general graph, or at least not a kind of obvious or canonical one, and so we can just take this as the graph spectral convolution as a definition for convolution, and live with it. But even that is a bit, it's not that satisfying, because there is still this dependency on choice of basis, right? And on this basis B of eigenvectors for the graph Laplacian. And while on the circle the Fourier basis was kind of well, given, where here by given I sort of mean somebody told us about it in math class. But later on I'll elaborate a little bit on what this given means. I think this is one of the more interesting points about convolutions and Fourier series. I won't be able to go too much in detail there, but if you're interested, you can follow. You can research this a little bit, and at least this Fourier basis was kind of given. But in the graph case, we really have to choose the basis B by which to diagonalize the Laplace operator, and this choice is really kind of very essential to what result we get. So one fairly easy check you can make is that if you choose the basis minus B, right, we just can multiply all of them by -1, and then the resulting convolution will also multiply by -1. Okay, and that's just what happens if we just multiply by -1. But what happens if we just flip the signs of just some of the basis elements, or what if the Laplacian has repeated eigenvalues, and then we can just apply orthogonal transformations to orthonormal bases of these eigenspaces and get completely new bases. And well, the result is dramatically different. So hopefully by the end of this tutorial, we'll be able to show you an example of this. So we have this dependence on the basis. There is some kind of importance for the Fourier basis on the on the circle. And we also, on a general graph, there's no shift operation, so it's not like there is a ground truth convolution that we can compare the spectral convolution to. However, on sufficiently simple examples, you might have a natural shift operation, and then you can define a different kind of convolution and try to compare those. So we'll look at the simplest possible example for this situation. And so we'll actually have a look at a graph, a circular graph like this, an n-gon. Now, the motivations for this example, as I already mentioned, well, one is that, well, the whole story about spectral graph convolution was motivated by the circle, and so we can try to approximate the circle by graphs, and then try and see whether applying this graph spectral convolution converges in any meaningful way to applying a smooth convolution on the result. So here is a kind of more precise way to phrase this question. Well, what? Well, but we saw, I mean, this convergence question, we also have to say, okay, which graph spectral convolution we're going to look at and ask about convergence, because they depend on this choice of basis. So the one sort of well-posed question is, well, what, if any, is the correct basis Bn of eigenfunctions of the graph Laplacian on an n-gon such that if f and g are two functions on the circle, we have that, well, we can first restrict the functions to the n-gon and then perform the spectral graph convolution, or we can just convolve them on the circle using the shift action on the circle and then restrict to the n-gon. And so what are the bases in which these things converge? And now let me just label this graph a little bit. I'm going to label its vertices like this. So this one is going to be 1, and otherwise t to the 0. So t1, t squared, t cubed, t to the 4th, and t to the 5th. So this representation is kind of useful because we can easily represent the shift action as just multiplication by t. Of course, we have to read the exponents here, modulo 6. And so on the n-gon itself, we have this shift action that's just multiplication by t. And so we can ask, we can define the convolution just on the n-gon in that case. And this one is kind of canonically defined. So we can just, if you give me two functions on the n-gon, we can just define this to be the sum of j of the function evaluated at t to the j, the first one, and the second one evaluated at I minus j. So this is at t to the I. So we can define a convolution in this way, and well, let me just normalize it as well. So I'm going to divide by n here. And so now we can just compare this convolution to the spectral graph convolution just on the n-gon without going to the limits of the circle. So we still get the question, what, if any, is the correct basis Bn of eigenvectors of the graph Laplacian gamma n, such that, well, the convolution defined using shifts is the same as the convolution defined using the spectral graph convolution. All right, so I mean, these questions, their answers are probably not that big a secret to most of you, because this is, there is of course a kind of discrete Fourier basis, and it's the one that will work in both these cases, and you know, of course, kind of discrete Fourier transform would show up in this discussion. So the answers to these questions are not particularly suspenseful, but you know, in fact, yes, there exist these discrete Fourier bases, and they approximate the Fourier basis on the circle. But as I mentioned earlier, you know, I think one of the deeper questions that one can ask is, but what makes the Fourier basis so special? Because actually, I keep doing this. Actually, you know, even on the circle, so even in the kind of the base of our analogy, the Fourier basis, yes, it behaves really well with convolution, but it wasn't the only basis we could have picked. Because if you noticed, the Fourier basis elements chi-m and chi-m, they belong to the same eigenspace of the Laplacian on the circle. The eigenvalue was 2 pi m squared. And so, you know, why did we choose these ones? Why not some orthogonal transformation of them, like maybe these guys? Why don't these ones give us such a nice convolution theorem? So there is a more general phenomenon at play here. It's not just that we're taking the eigenbasis of a Laplacian, and to explain this more general phenomenon is, you know, not something that I can do in this tutorial, but it's it has to do with representations of compact Lie groups. So if you're interested, you can Google some of these terms as compact Lie groups. And there's also something called the Peter-Weyl theorem, which are really interesting theorems, kind of expanding this idea of a Fourier basis to more general manifolds equipped with a shift operation, so manifolds where there is a natural notion of convolution. Okay, so but without delving deeper into that, let's just get our hands dirty and try to compute the spectral convolution on an angle and find the Fourier basis for ourselves. Right, so first we need to determine the Laplacian, so we start with the adjacency matrix. Well, the adjacency matrix is, it looks something like this. So every node is only connected to its two neighbors, and so on. Okay, and the rest is zeros. And the degree matrix is even simpler than that, because every node has exactly the same degree. It's just a multiple of the identity. Okay, and because it's the multiple of the identity, we don't need to diagonalize delta. It's equivalent to diagonalizing A, or in fact 1/2 A, just because it makes the calculations a little bit easier. So I'm just going to denote the matrix 1/2 A as T. And so let's try to diagonalize this matrix. So start by just writing the eigenvector-eigenvalue equation like so. But before we do that, let's just suppose that X is an eigenvector of T, and just consider the following situation. So just consider lambda squared times the sum of xj squared. So we just take the outer norm of xj multiplied by lambda squared. Now, because x is an eigenvector, that's the same as tx, this norm of tx, and you can expand this to, well, it's equal to that, where here the indices are again read modulo n, and then there's an easy inequality to see that this is less than or equal to that. And again, thinking about what are the what the sum is, in keeping in mind that we have to read the indices modulo n, we recover this. So from this calculation, we see that lambda times the squared norm of x is equal to is less than or equal to the squared norm of x. Right. So we just get that lambda squared is less than or equal to 1. And as another kind of computational and convenience trick, that means that we can set lambda to be cos theta, percent theta. Okay, and then these computational tricks out of the way, what does the eigenvector equation look like? Well, it looks like it's xj minus 1 plus xj plus 1 over 2 must equal to cos theta xj. Or rearranging this, we arrive at a recurrence relation. It looks like this. Okay, and how do we solve recurrence relations like that? Well, we look at the characteristic equations, and in this case, the characteristic equation is just that. And thankfully, this one factorizes really easily, thanks to all the computational tricks we did in the beginning. It factorizes like that. Okay, so then the general theory about recurrence relations tells us that the general solution to our recurrence relation is given by a linear combination like so. Minus I theta j. But of course, this was just for a general sequence xj. We want our sequence to actually give us an eigenvector of t, and so we need xn to be equal to x0, because we need the indices to be able to read the indices modulo n. And it is easily seen that you can achieve this by theta n should be equal to 2 pi m for some m, or in other words, theta is 2 pi m over n for some m in 0 to n minus 1. Okay, and so I know this was a bit fast, but it's not particularly difficult calculation to do. And so in the end, we end up with an eigenvalue lambda m. Remember, lambda was cos theta, so it's cos 2 pi m over n, and it has an associated eigenvector given this m over n, and then it's e to the 2 pi I 2m over n. So yeah, great. So this we have our eigenbasis now, but notice that. Well, first notice that this really is the discrete Fourier basis, because well chi m now xm at tj, thinking of x now as a function on the angle, so this is just the jth element, is the same thing as chi m. So it really is kind of the restriction of the Fourier basis to the n-gon. But again, we have this problem with multiple eigenvalues. So when n is even, we get two simple eigenvalues, which lambda 0 and, equals 1, and lambda n over 2, which is minus 1, because this cost that we're taking here gets the same value for m equal to 0 and n over 2. And the rest of the eigenvalues are double. And for n odd, we get a single simple eigenvalue, lambda 0 equals 1, and all the other eigenvalues are double. So again, we had a choice of basis that had to be made, and we arrived at it by just using this fundamental solution here of the recurrence relation, but we could have used some slightly different method. Or if we, for example, if we were looking for only real eigenvectors, we would have never arrived at the solution. And so, okay, so remember the questions that we asked. So the second question was, okay, how does the convolution in terms of shifts of the n-gon relate to the spectral convolution? And we can happily report that for this particular basis, they indeed agree. I'm not going to take you through the calculation, but it's here, and it's just relatively simple, apart from a slightly interesting exercise to show that this term here is 1 if n equals n prime and 0 otherwise. And so indeed, so this discrete Fourier basis was the correct basis, and we arrived at it by just taking the graph Laplacian and trying to diagonalize it in some way. Now, as for question 1, whether we would get convergence to the smooth convolution if we make the n-gon finer and finer, then, well, we can now reasonably expect this for this Fourier basis because of this relation, right? Once we saw that we really get the just finer and finer evaluations of the smooth Fourier basis, to get the discrete one, we can expect this to happen. And actually, Daniel here ran an experiment because the pictures are prettier. He ran it on a 2 torus rather than a circle, so the product of 2 circles. And here are some of the results. So we plug in 2 functions, f and g. We take the smooth convolution on the 2 torus using the shift operation there. We take the spectrograph convolution with respect to this Fourier basis. And the last column here is we take spectral graph convolution, but we just allow SciPy to diagonalize the graph Laplacian for us. So whatever basis SciPy finds, that's the one we use. And you can see that in most cases, well, in all cases, the graph Fourier convolution agrees with the smooth convolution, at least for sufficiently large n. While on the other hand, the one that we get by just using the basis from Spacey is kind of arbitrary. It's, you can see here we're convolving a function that's constant in y with a function that's constant in x, so the result is a constant function altogether. Not so for the convolution with the basis that Spacey finds. In some cases, though, it does agree, like here. So we got lucky there, but you can see that the dependence on the basis is really rather drastic. Okay, well that's me. I think I'm all out of time, and I'm happy to answer questions if you have any.